Hello and welcome. I'm continuing with videos from a paper I wrote very recently, the Mechanics Statistics paper S, which contains difficult questions overall, enrichment mainly. And I've done 3 videos so far, 2 from the stats section, and I'm going to do 3 from the mechanics. I've done this vector question already on a previous video. I don't necessarily say I'm going to upload them in the same order. And now I'm going to do question 9, which is a question on calculus kinematics. I'll read it and then I will record the information down. Particle P is moving on the x-axis, its velocity v meters per second in the positive x direction. T seconds after a given instant is given by this quadratic. The particle is passing through the origin when t is equal to 0. Determine the displacement of the particle from the origin when it has covered a total distance in bold of 13 meters. Okay, I think I'm going to move the paper away and I'm going to record on the side. And that's how you should do your mechanics. I mean, read the question. Sometimes with long questions, don't read the whole thing from beginning to end. Nothing will go in. Okay, identify what the topic is and then slowly go back to the question and start recording the bits which are important. V is a half t squared. This is like differentiation and integration backwards, but I'm going to do it because, of course, it's a sensible way of doing this question. Is not actually to be doing this. It's actually a very good way of doing it, the way I'm going to show you. So, and it's telling us that the particle is passing through the origin when t is equal to 0. Is to do, if you're going to attempt this question by integrating backwards to get displacements and all sorts. This is a condition. When t is equal to 0, is passing through the origin, so x is equal to 0, and is asking us to find the displacement of the particle, x equals question mark, when total distance is 13. If you do with differentiation integration, I'm not going to show this method. I'm getting a little bit tired today to be showing alternatives. It's going to be quite a complicated thing, but I want to illustrate a couple of things. This is a velocity time graph or a speed time graph at elementary level, but this is not one that you normally be taught how to do in your mechanics, because you stick with this kind of like cars and motorcycles, like kind of accelerated uniformly and they're going across and the usual stuff. So the first thing I want to do is I'm going to take this velocity expression and I'm going to sketch it and set it equal to 0 to find where it crosses the t-axis. You'll see in a minute where this is heading. This is nothing to do with mechanics. That's purely to sketch the graph. Double it. Factorize it. 4 times 2. So it crosses the t-axis at 2 and 4. So this is what we've got. We've got 2, 4. Somewhere here is there's no more, of course, there because t has to be positive. So that's your t-axis or your x-axis, and this is your velocity axis. And this, of course, is a velocity time graph. It's just that you don't often see this. And they're very, very useful for calculus kinematics questions. A good proportion, I wouldn't say more than half, but a good proportion can be solved quicker and more effectively by considering the graph, basically. So they're actually saying to us to find the displacement from the origin when the total distance doesn't matter. So for example, if this turned out to be 5 and this area is -6, the displacement by the time you hit there is of course 5 minus 6, which is -1. That's displacement, but distance is in fact 11. So we'll see how we're going to use that. First of all, let's integrate. And we're integrating the velocity to get displacement. So I'm going to get a general expression. So, and then I'm going to be putting limits minus 3t. No, sorry, not minus 3t. Not even that, I'm writing stupid things. I do apologize. I'm getting ahead of my head. Still integration. So I'm putting the expression under the integral sign. And this is going to be t1 to t2. t1 to t2. And then when we're integrating, we're going to get 1/6 t cubed minus 3 over 2t squared plus 4t from t1 to t2. So depending on where we integrate, we can stick the appropriate limits. So the first of all, let's use a different color pen here. Something bright, pink will do. So this is A1, and this is A2, and we'll see what we got so far. Okay, so A1, quite clearly, is the integral, not the integral, because I have an expression for that. 1/6 cubed minus 3 over 2t squared plus 4t between 0 and 2. 8 over 6, 4/3. 4, 1/2 times 4 is minus 6, plus 8, which is 2, plus 4/3, 6 10/3. So A1, this bit here, the particle has moved a distance of 10/3 and the displacement is also 10/3. Now we go to A2. A2 is, of course, exactly the same integrated quantity, because I've already done it. But now we're from 2 to 4. 464 over 6, 32 over 3. 416, 1/2 times 16 is 24. And then we got, of course, 4 times 4, which is 16. And if we put 2 in there, we should really get the 10/3 that we got from before, but you can actually write it the long way. 32/3, take away 10/3 is 22/3. And this is a minus 8. 22, 24, I'm making that minus 2/3. So this bit here, as expected, it's going to be negative. And it's going to be, of course, below the x-axis. Now, what have we got so far? In the first 4 seconds, this particle has a displacement when t is equal to 4, just to understand the interpretation of this. By the time we've done all of this, at t is equal to 4, the displacement is equal to minus 2/3, but the distance that it has traveled is in fact 10/3 minus 2/3, or quite stupidly, it has covered 2/3 and 10/3, 12/3 is actually 4 meters. So in fact, what do we need to know? The particles at t is equal to 4. We can actually write the answer now, essentially. The particle is reached this stage here, and it has covered a distance of 4. We want to know the displacement of the particle when the total distance is 9. So it needs to cover another 13 take away 4, 9 meters. And of course, I don't need calculus for that. It doesn't ask for the time. I need to know, or the A3 rather, from there to some kind of time, which is going to be bigger than 4. I need another 9. That would give me, of course, a total of 13 meters in distance, but the displacement now is going to be 9. And therefore, there is nothing to write on this one other than required this is a little bit kind of displacement. Required displacement is 9. I would imagine students might be struggling a little bit to grasp that last bit, but have a little think about it. I'll repeat it out just very, very quickly. We're looking up to 4 seconds. Up to 4 seconds, the total distance is this area and this area, and this area is 10/3 add 2/3, which is 4 meters. So it means we need another 9 meters distance to be covered, but we're at 4 meters and the graph now is going positive. So it doesn't really matter. If the question asks us, of course, what is the time, we need to find this bit here. So we have a little bit more calculus to do, a little bit more algebra. But at the moment, all of this is now going to be the displacement at some time, I don't know, 6, 7 seconds. And this is now the displacement of the particle, 9 meters, that is required. Okay, I hope you followed this. And I'm going to do one more question from this particular paper, which I'm not quite sure what topic it is. For the time being, I'm signing out and I'll see you real soon. Bye.